Okay, so this is one of three short-ish talks on water quality. This one introduces the very basics of water and water chemistry. And usually, textbooks on water chemistry will start by introducing the water molecule. And so this is a conceptual model of a water molecule. It looks like a Mickey Mouse character here, but there are some very unique properties of water. We take water for granted, obviously, like it's a common substance, but it's really got some very interesting and unique properties. And the first one here that is illustrated on this picture is because of the way that the two hydrogens are arranged with the oxygen molecule. That's what water is two hydrogens in a water, H2O. But the hydrogens tend to ball up on one side of the molecule. And so when you have hydrogen carries more of a positive charge, the positive charge of the hydrogen tends to accumulate on one side of the molecule, and so that ends up being positive, and the other side is negative. And that is makes water gives water a lot of its properties. It's bipolar. There's a lot of connotations to that term, but just to say one side is charged relative to the other. And what that results in, here are these teddy bear models all over the place now. Here's a molecule. The big thing is the oxygen, the two little pluses of the two hydrogens. And because one side is negative and one side is positive, the molecules themselves tend to cling together very closely, and they form what is called a hydrogen bond. Now, that's not really a bond like in classic chemistry, a covalent bond, or maybe you've learned about those, but it's just rather that this plus charge of the hydrogen and the negative side of the oxygen attract each other and they stick together. And that bond is very hard to break. It takes a lot of energy to pull two water molecules apart because of this strange configuration that they have. And that gives water a lot of its properties. For one thing, it makes it take a lot of energy to go from liquid to vapor because you are breaking apart that bond. And it causes that process to either consume or release a great deal of energy. So this is a slide I like to show you how much energy is involved with water and the changing phases of water. And a large reason for that is this hydrogen bond. So if you start with, on the left side here, 1 gram of ice. It's frozen, obviously. It takes 80 calories to get it to liquid state. Just to go from solid to liquid takes 80 calories of energy. This is still droplet at 0 degrees. This is at 0 degrees in the ice cube. This is at 0 degrees in liquid. It took 80 calories just to get it from solid to liquid. Here's another one. It takes 100 calories to get it from 0 degrees liquid to 100 degrees Celsius, which is boiling. So just heating up the water that much, 100 calories. But then here's the biggie. It's 540 calories to get it to go from 100 degrees liquid to change phase into that vapor. So this this water vapor is 100 degrees Celsius. This drop of water is 100 degrees Celsius. But just breaking those bonds consumes a tremendous amount of energy. And that is how a great, this also explains why when you go from vapor to water, you release that 540. But this explains why you get so much cooling when you sweat and evaporate. When you go from liquid to vapor, all those calories are absorbed into the vapor, and that heat energy leaves your body and it cools you off. All these unique features are due in large extent to that hydrogen bonding property of water. And lastly, the super unique property of water is that its solid phase is less dense than its liquid phase. all other substances, kind of like water, the colder you get, the more you reduce the temperature of a substance, the more dense it gets. The molecules are closer together. Totally makes sense. Water's the same way. As you go from warm water to cool water, the molecules are just closer together because they're vibrating less, they're bouncing off each other less. Makes sense. What's bizarre about water, and this isn't really about the hydrogen bond, it's just another strange property. When you do that phase change from liquid to solid, then it assumes this lattice structure that just so happens to be less dense than the cold water. So the water gets denser and denser and colder and colder. Then when it changes phase, the ice uh, assumes solid phase and gets less dense and floats on the top. And you probably are familiar with this. The significance of this is that we have many, many lakes that freeze over, and yet you have liquid water underneath the ice and a lot of aquatic life through the winter. But I want to focus more on the basic chemistry of water and how water dissolves chemicals, how contaminants get in the water, and then ultimately what we'll learn is how we remove those chemicals from the water so it's safe for us to use. The figure on the left I want to talk about, but first the figure on the right is just the last little side note here. Water is a lot more dense than one would make it out to be. And one model that is floating around the literature is this ice cluster model where there's temporary formed ice structures in the water at any given time that flicker in and out of existence. Um, I tell you, water is a strange substance, and if you get into the literature on the chemistry of water, it's very very interesting. Don't take it for granted. More important here is this diagram to the left, and this illustrates, and the next couple of slides illustrate how water can dissolve salts and minerals so well. They call it a universal solvent. A solvent is something that dissolves things. And the basic definition of a salt, like let's take the simplest salt, sodium chloride, is it consists of a positive atom. In this case, the sodium atom is positively charged, and a negative atom, the chloride. Water loves that because it'll take that sodium chloride, break it apart, and you see how all the O's are lined up next to the positive sodium? That's because the O's are negatively charged. And so the water loves the charged particle because it is charged itself, and the negative and the positive line up. And literally, what happens is the sodium molecule gets surrounded by a couple of layers of water molecules very tightly stuck to it electrically. And then finally, about 8 or 10 layers of water molecules away, you'll get into kind of regular water. But this is what the sodium looks like when it's dissolved in water. Here's another cartoon of it. Let's say you had sodium chloride, which is this green and blue. Chloride is green with a negative charge, and the blue is sodium with a positive charge. Let's say it's a granular gram of salt. You put it in the water, and what the water will do is pull these things apart in effect, and take these pluses and surround them with negative charged the sides of water molecules, and it'll take the minus chloride and surround it with the positive ends of the water molecules. And that is what salt looks like when it's dissolved in water. It's completely part of the water at this point. And as we'll see, very difficult to remove if you wanted to get it out of the water. This is in contrast with organic chemicals. So I think Water 4.0, or one of the water chapters here that you're reading, talks about the difference between inorganic and organic. That's an old term, organic chemistry. It was meant to say we're studying the chemistry of living things or organisms, organic chemistry. The current meaning is a little different than that. But for us, there's a very big difference between chemicals that have this positive and negative polarity and charge and how they are very dissolvable in water, and organic molecules that don't. So if you take salt, put it in water, it disappears, it dissolves completely. If you take an organic molecule that doesn't have that charge structure, it tends not to dissolve. Oil and water don't mix. Not quite completely true, it's just that the solubility, the ability of the organic molecule to dissolve in water is low because organic molecules aren't charged like that. They're neutral. And so the water is like kind of indifferent to them too, doesn't like to dissolve as much. And one way to illustrate this is sort of the chemistry of how soap works. And it's really kind of cool because what the soap molecule does is it has a big organic part to it, a hydrocarbon tail, they call it, which is organic molecule that is not charged. And it has at the end of it an inorganic part, sort of, that is charged. So the significance of this is that organic chemicals tend to dissolve in other organic chemicals, and charged particles tend to dissolve in the water. So what the soap does is you put it on your body, and let's say your skin has a bunch of nasty and junky oils, and the oil on your skin will dissolve into this oil part of the soap molecule. Okay, then when you wash off with water, that water will dissolve this whole oily, fatty molecule because it has a charged end to it. And so the water sort of pulls all out in, and that's how soap works. It's just a way to illustrate the difference between organic chemicals with carbon and hydrogen and no charge, and inorganic chemicals that we can say are salts. This is just another cartoon of the same thing. Polar end mixes with water. A better way to say it, it dissolves in the water. Here's the nonpolar end, dissolves fat. So this pulls the fat off your skin, and this dissolves that whole glob into the water and washes it off. There's another diagram of the same thing. And so the significance of this is how water is treated. If your water is contaminated with an organic chemical, then what you want to do is filter that water through something else that's organic. Like in this case, this is a picture of granular activated carbon, which is literally just like basically charred wood. It's one of the oldest methods to treat water. I mean, we're talking millennia old, that people discovered that when you take nasty water and percolate it through charcoal, it comes out much better on the other end. And this is a technology that is used big time to this day. Obviously, we're very sophisticated in how to make this organic carbon, but it is still the basically plant matter that's burned and crushed, and you filter water through it. And so what happens is the organic molecules in the water trickle through this stuff, and they either find their way in these little micropores of the granular carbon, or they sort of just dissolve, so to speak, into the organic carbon. So the point is, if you had sodium chloride in your water, if you had a bunch of salty water and you filtered it through organic carbon, it would just pass right through. Not a single salt molecule would be filtered out. But if you had an organic chemical, say benzene or trichloroethylene or some of these organic solvents, sure, when the water with that solvent mixed into it, dissolved into it, hits this carbon, the organic molecule is much happier getting out of the water and sticking to the carbon. And that's how it works. And it works really well. It's like I say, it's very ancient, but still used to this day. This is how you would build we don't just get a bucket of charcoal and drip water through it. It looks a little more official this way. This diagram just says we just shove the water through a tank with carbon and it comes out clean. This is what it looks like on the ground. These are big tanks. They're just full of charcoal, high quality, highly engineered charcoal, but it's just charcoal. And the pipe shoves the water in, it passes through, goes to the next one, goes to the next one, and they typically what a water treatment plant will do is they'll start, the worst water will come in first, go through the first chamber to the second, and then this will be polished. And then when this first tank is trashed, because you can imagine after a long period of time, all these places in the carbon for the organic molecule to fit get taken up. And this carbon then gets used. And the bad water comes in, and it comes, as soon as it passes through, you get rid of this carbon, and you take this carbon and put it in the middle. It's like you know, I'm sorry, you swap out the bad carbon, it goes away. This good carbon goes in the front, and then the brand new carbon goes to the polishing. It's kind of like changing tires on a car. You know, the tires that are trash get replaced, and the okay tires get rotated to the front or whatever. And this is, like I say, very, very common for treating contaminated water at contaminated sites, or pre-treating water for drinking in cases. But back to the salts. Like I say, if this water here with this sodium molecule in the middle of it went through this carbon, it would just shoot right out, all three. It wouldn't touch it. So if you have a bunch of salt in the water, dissolved like this, I mean, really in there molecularly, and you had too much salt, let's say you had seawater intrusion, and you wanted to use that water, what would you do? And this is the area of desalination, which you've probably heard about. And old school desalination, it's not entirely old school. Some people are still working on this. One way to do it is just to literally boil the water and have the water go from liquid phase to vapor phase. When that happens, the salts get left behind. This is the same thing this is called evapoconcentration, which is a very important term to learn. This is what happens when the ocean is salty, and then the winds blow by, and you've got nice water vapor coming off. There's without salt in the water vapor. When water evaporates, the water part goes, the salts stay behind. And so, using that principle, this is just a fancy way of taking water with a bunch of salts, you heat it up. This produced water, this is the good stuff, it's condensed and it comes out. And what you're left with is a bunch of what ultimately brine. You can imagine if you had seawater, you boiled it, you got the good clean vapor off. After a while, you're going to end up with pretty nasty brine because you had seawater before. Now you took a lot of the water out of that seawater, the H2O. You're left with a pretty sludgy, salty brine. This takes a lot of energy. It's not very efficient. The current technology is called reverse osmosis. And this technology is widely being used and expanded, and is a lot of ways a big part of our future, because with this technology, you can take water with salt in it, push it through a very fine, it amounts to just be a very fine filter, and the salts stay behind and the H2O molecules go through. That's the basic principle. We're talking about new materials, graphene, nanomaterials, to make some people call it a molecular sieve, a screen, in effect, that's so small that a water molecule that has a bunch of a sodium atom surrounded by water won't go through, but a water molecule all by itself can fit through. This is a better diagram, a little cartoon. In this cartoon, they look like little prescription pills. I don't know why they did that, but these are water molecules. They can pass through. These gold balls, that could be a chlorine atom or a sodium atom with water surrounding it. It won't go through. Or it could be a molecule, a contaminant, some big nasty molecule, a hormone in our system, Tylenol, vitamins, stuff we don't like in our water. It's going to be bigger than a water molecule, and it gets trapped behind the filter. The real filters end up looking like this. It's a complicated design, but if you go to a water treatment plant that does reverse osmosis, you'll see stacks and stacks of these tubes that the permeate. The good water comes out the middle, and the concentrate, the junk that you don't want that didn't make it through the filter, also gets produced. You definitely produce waste, and that's kind of a problem. What do you do with this yucky, nasty water after you squeeze the good water out of it? Definitely a concern with this technology. But this is just to say, this is the future. This is, the reverse osmosis is how you can take water with salt. You can take ocean water right out of the ocean, shove it through this molecular sieve by reverse osmosis, and the salty molecules will stay behind and the H2O will come through. It works. It takes a lot of energy to do this. You can imagine that the salty water doesn't want to flow through this filter at all. You have to shove it through with energy, and they're working on how to make it more and more efficient. But anyways, reverse osmosis is a big deal. When we go into toilet to tap, and we're taking our sewage, one of my favorite topics, the stuff you flush down the toilet. And when a vet clinic or a hospital takes a corpse and dissolves it in acids and puts it down the sewer, that kind of stuff. And we treat it and treat it and treat it. And this is one of the polishing steps. You run that water through this molecular sieve. So any nasty chemical, the concept is any nasty molecule that you don't want won't make it through the sieve. After you have this pure water, believe it or not, there's like 2 or 3 other stages of treatment that are typically done on this pure water to further kill any viruses or bacteria that may possibly have made it through the sieve, just in case. So these extra steps are taken to kind of comfort people that this water is actually okay to drink. And this is all to say, this is not theoretical. This is all technologies that are being used. You can get these at Culligan. There's limitations to doing it under your sink, but let's see. So this example is a 3-chamber. This one just filters sediment out of the water. Then it might go through this carbon filter. This carbon block is just a carbon filter. You can get Brita filters that are just carbon. And then this is a reverse osmosis filter that just uses the pressure of water in your house to shove it through a molecular sieve, and you'll come out with mighty clean and treated water. So I hope that's helpful and clear enough.